Okay. So, folks, we are interested in the Euler equation on a manifold. So we take a smooth Riemannian manifold and you take a Levibach connection and velocity field, which evolves by transport with a pressure and construct. You can also add viscosity, get the Navier-Stokes equations, but I have nothing new to say about Navier-Stokes. So Euler. Okay, so this equation, it has a very strong geometry. If you phrase it in terms of the one form, so if you change the velocity u to the dual one form, I think other talks call it lambda. I call it v. The velocity dual one form, the Euler equations take this form, that the one form co-velocity gets transported by the velocity. So the time derivative is transported by the Lie derivative of the one form with respect to the velocity with the modified pressure. So the pressure you have to modify by 1/2 the energy density. So you can also write the Euler equations in this form. And then the advantage of this form is that you can then take an exterior derivative and kill the pressure. And then if you define the vorticity 2 form to be the derivative of the one form, then you get a simpler equation. So the Euler equations also transport the vorticity. The vorticity 2 form is transported by the velocity, now with no force. And then you can recover because you have the you can recover the velocity from the vorticity by inverting some operator. Okay, so the velocity is determined from the vorticity by the Bauer-Savart law, and it's basically okay. So this is what's called the vorticity stream form of the. So it's a very geometric equation, and so one consequence of this is that this equation conserves a lot of quantity. So it's homogeneous. Actually, it conserves many other things as well. Okay, so first of all, it conserves the kinetic energy, which is just 1/2 the velocity squared integrated manifold. Circulation, because the vorticity is transported by the flow. If you integrate the vorticity on any two manifold, any surface, and then you transport the surface by or by Stokes' theorem, that's the same as integrating the velocity on the boundary of your surface, that is conserved. So the conservation of circulation, Kelvin's law. And then if your manifold has symmetries, you also get conserved momenta. So if your manifold happens to have a killing vector field Z, if you contract Z against your one form, I think people call it, other talks call it iota Z. These are conserved as well. So for example, in Euclidean space, you can take translation vector fields and then you can conserve linear momentum. You can also take rotation vector fields and angular momentum. Okay, so you get a lot of these. Helicity. So in odd dimensions, you can D-1, 2, and then you get a D-1 form, and then you can wedge it with the co-velocity, and now you get a volume form, and you integrate, and that gives you. So in 3 dimensions, that would just be velocity cross product vorticity. The same works in higher order. And even in even dimensions, there's a less known conserved quantity, but you also get a conserved quantity in even dimensions. An even dimension, and then you get a volume form just on the nose, and you integrate that. also concerned. Okay. And all these conservation laws can be sort of explained in some sense by this lovely observation of Arnold, which was already mentioned in Ross's talk, that you can think of the as it's just geodesic in the um, diffeomorphisms on M. That's an infinite dimensional manifold. You can put an L2 metric on it, a metric, formally geodesic flow. And all of these symmetries come from various symmetries of this manifold. So the conservation of circulation comes from change of variables in conservation momenta come from change of variables in Eulerian coordinates. So these are very geometric equations. So quantities. It's increasingly believed that these equations blow. So we have this conjecture, which we are getting closer and closer to actually establishing. People are most interested in flat R3, but I'll state it. A weaker form of the conjecture is that there should exist at least one of some dimension and smooth in theta at enough decay if manifold is not compact, enough decay that you're not blowing up just because of infinite energy or something. To these Euler equations that develop singularity in finite time. Okay, so this is basically what we believe to be true. So R3, because that's the space where we live in. But it should be possible. I mean, it should be easier to prove this conjecture. So if we don't constrain the dimension, because higher dimensions should be worse, more likely to blow up. But also, if we get to choose the metric, then maybe we can use the metric to somehow make it easier to make a blow up solution. And we have a number of results that sort of support now the belief that the metric, you can the Euler equations become very somehow you can prescribe all kinds of the Euler equations that the Euler equation anything that a computer can. Okay, and so if you can get a computer to blow up, okay, then you can replicate the Euler equations to blow up as well. All right, that's sort of the idea. Now I'm focusing here on smooth solutions. I just although it's not really the focus of this lecture, but it was many. There are many results on if you allow for singularities, mild singularities in your initial data. We can already make all the equations blow up. So that's years back in R3, you can blow up. There's initial data which is just wholly continuous, which leaves C1 alpha in finite time. So it's have to get local existence, but does not imply global existence. Yeah, but here it was really important that there was a singularity. The singularity really sort of make completion. And that was a way to construct these the blow-up solution, which is recently given by Kodoba, Martinez, and Zhang, which was mentioned in his talk. There's also progress on complex integration techniques to construct weak solutions to Euler equations and all kinds of bad things of energy conservation. These are quite you can make them give them some sort of regularity, but not very much. But yeah, but these are formed by sort of you start with a low regularity approximate solution, and then correct it by adding a higher frequency correction. So yeah, solution, but not a strong. And we have, as we saw with talks on Tuesday, we have a number of ways to construct blow-up. You can for the axis or outside of us. Okay, so we're getting a number of blow-up results now, but not on a smooth manifold with smooth data yet. And then last another near miss to this conjecture by Cordoba. You also mentioned it. And can, well, back in R3 to the Euler equations where the initial data is smooth and the forcing data is smooth, but it gets less smooth as you push the blow up time. It's uniformly, again, in a Holder class C1 alpha, at any given time, it's in infinity, but only the C1 alpha norm stays bounded. Okay, so yeah, so Diego already mentioned construction. Again, you have a solution that sort of starts concentrating at one scale, and then you insert a little forcing term at a much higher scale, and then it gets stretched from the previous solution to become much up, another little bubble, and you insert. Um, yeah, it's a very nice construction. It becomes somehow very close to something that's conjecture, except that this is forcing, which is not so clear how to show. Okay. Um, ago, I showed that the Euler equations could somehow blow up. That if you okay, so in previous way, you can making the regularities. You can cheat by adding a fourth term. You can also cheat by changing laws of physics. Um, um, is given from the vorticity by the Bauer law. And some other has a Hamiltonian form. It still preserves circulation, preserves energy. It has many of the Euler equation, but it's not the Euler equation. Uh, but somehow is that you can't prove global regularity just by uh, this modified operator obeys the same estimates. Um, if regularity is true, you have to use a property specific to the Euler equations, which sort of these more general equations do not have. So, I think conservation of or vortex stretching is not enough to prove coexistence. So the way I prove blow up here is you sort of normally you start with a PDE and then you solve it and you get your solution. But once you have the freedom to change the laws of physics, you can do it in reverse. You write down the solution, like you give that solution. It's not quite as simple as it sounds, but that really kind of yeah, the I just write down a blow up ansatz and then I find so it's a vortex neck pinch example, but maybe it's easier to explain using a picture. Um, right. What this solution does is that like a laminar, like I, I choose the Balsavallo to keep pushing the vorticity. The velocity is it will to keep it divergence free. It will then poke outwards down here. Oops. Um, one and as you put one minus t becomes small, the little disk of diameter about square root 1 minus one minus t, the minus t. I think the vorticity is 1 over 1 minus t. It blows up at a very prescribed rate. So this is not the type of blow up that we see. So the previous blow up constructions of various Euler type equations don't have this particular vortex tube pinching type phenomenon. So this is in some sense a quite artificial example. Although I will point out that there's some intriguing numerics. There's some they get thin um, phenomenon. Yeah, unfortunately, they also get very tangled. So it's as this next pinch that that I will some evidence, numerical evidence that keeps. There was sort of at least two iterations of yeah, there's if they pinch, they get tangled, and then they pinch again, and then at that point they ran out of numerical capacity to simulate what happens next. Yeah, but there is some possibility that you could make a neck pinch type singularity rigorous, possibly, but I was never able to take it much further. That's what I'm looking to. Okay, so as I said, you can cheat by changing laws of physics. Uh, a more realistic cheat is to change the metric of the geometry, showing what the Euler. Um, so one of the first things I was able to do, just by playing on it with explicit constructions, actually, is to show that the dynamics on an arbitrary the Euler is at least as complicated as sort of an arbitrary quadratic ODE, except that you always have to conserve energy. Okay, so there always has to be some conservation law. No matter what, there has to be something that has to keep things bounded somehow. So if you take any quadratic ODE, so U is now not living, not a divergence-free vector field, but living in some finite dimensional vector space. You can take any quadratic ODE, but not that would blow up in finite time. You can't take dt equals u squared. But if you take one that obeys a conservation law, that the BUU is the quadratic form is always orthogonal to u, the magnitude of your velocity, um, that's energy conservation. Then this dynamics appears somehow. You can embed this dynamics into the Euler dynamics of some manifold. There's linear form B. You can find a manifold depending on B, and you can find a way to identify vectors in your vector space with divergence in on your manifold, so that this is just the Euler dynamics. Yeah, so every quadratic ODE that has a conservation law can be realized as a solution, can be converted to a solution Euler equations. Something like if I could make the Riccati equation dt equals u squared embed here, but it was never going to be easy. Right. I mean, on any finite dimensional dynamics will never blow up, because on a finite dimensional space, all norms are equivalent. And if once you conserve energy, that will bound. Then you have a bound that you would be constrained to a compact space. Um, so this was a fairly rich set of dynamics as for yesterday. For other later. Okay. So yeah, there's explicit construction. So the manifold was explicitly actually just a product of an orthogonal group. Um, Basically, you down you down the explicit form of the dynamic. It's overdetermined. You that only n on you know it's miraculous that this thing exists at all. But it chose a metric to really cut down the number of equations I needed. And um, um, so that's one thing that I did. Another sense in which the okay, so any quadratic ODE can be embedded. I then looked at what about more general dynamics. So if you take any sort of for example, on a torus, you take any smooth vector field on a torus. Can you embed any smooth vector field on a torus into some Euler dynamics? And the answer is kind of. I showed, for example, that if you look at this sort of all smooth flows on a torus, there is a dense set of, or somewhere dense at least. Well, now it's actually known to be everywhere dense. Flows which you can embed into an Euler flow on some manifold, but the manifold depends on what the flow is. Uh, but not every first category. So in some sense, so it's dense. So every flow can be perturbed into something that is an Euler flow, but in fact most flows in some sense are not Euler flows. Um, okay. Um, 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 People have also studied, but also very interesting, and they're related contact geometry. So there's and both generate Beltrami flows. The Beltrami flows are examples of steady state Euler equations. Um, back also study Euler solutions. And what we there's a lot of state Euler flows. They also in some sense universal, like you know, type of behavior of a flow of a you could for shows up. Um, so, for example, if you have a vector field on a manifold which is divisible, which means that there's a metric on the manifold that turns the vector field in, then a vector field on a solution. Um, so that's not to say that the dynamics of this Euler flow behave like vector, because it's a stationary flow. The dynamics in this case are trivial. But the flow itself is also a vector field. So there's sort of two different vector fields. There's the sort of time and just following the velocity in space. But spatially, you can embed any dynamics you wish basically under this just one mild geodesical condition. Yeah. Okay. So again, yeah. So the main idea of proof is that these is to use the every it gives you a Trami just a flow. Uh, Machinery to generate flows. Yeah, and so yeah, one nice application of this is that solution Euler that the if you encode you can encode say a string of zeros and one. You can ask flow if you follow the flow lines. Do you maybe ever hit this halting region or not? And um, you can encode any question about the halting of any Turing machine as a question about a specific orbit region or not. In particular, the question whether an orbit one hits this region is undecidable. We'll disprove it. So yeah, so stationary Euler flows can be so arbitrarily nasty. Um, and this construction was done on a large manifold, but yeah, constructions in three dimensions, which I think I will not talk about here. Another sense in which stationary Euler solutions are somehow so there's every type, not every is, you can deform a vector which is a steady state of some. there's some embedding. So one consequence of this is that any topology you wish. Okay, in particular, you can create chaotic flows with positive topological entropy. So, okay, so that's what we know about stationary flows. And then going back to time-dependent flows, which is sort of what we need to understand blowup. Yeah, so the previous highlights I had were strengthened by Terence Tao, and he talked about this book yesterday, actually. Uh, on any compact manifold, we determine high-dimensional manifold M. Okay, so you can make an Euler flow which is within epsilon of your initial any epsilon. Yeah. So okay. So uh, we already talked about this yesterday, so I won't say too much about it. But yeah, I get so this in particular, you can start creating manifolds with which obey all kinds of robust dynamical property. Clinical, but you can um, dynamics. Okay. Okay. So this was already talked about yesterday, but yeah, it he first embeds the he shows that any dynamics can be sort of approximately embedded, modeled by a quadratic dynamics, and then I have this previous theorem that quadratic dynamics can be embedded in Euler. So it's sort of addition of these results. Okay. And one corollary of that is that yeah, so the Euler equations themselves are now known to be Turing complete. You know that if you want to if you want to know whether the specific high-dimensional manifold evolve this data, and it will the solution will enter this region if and only if the Turing machine holds. Uh, and so, in particular, there is no algorithm for determining whether this Euler will reach this region or not. Yeah, and this also answered this conjecture of Moore that had nothing to do with fluid dynamics. Yeah, so that yeah, more it implies that yeah, the form of iterating a diffeomorphism on a couple also can be. Okay. That, we can make the we, we can have Euler that do very so you know to make blow up solution at initial time that evolves maybe translated to one and so iterate again and again and you get a geometric series and you'll blow up infinite. So you could have a continuous self-similar blow up solution where your solution is always blowing up. It's a rescaled version of the initial data. But those probably don't exist for the other equations. Uh, um, that does one thing for one unit of time. So the rescaled version itself, uh, you're done. You get blow up. So, yeah, this rescaled than the induced algorithm. You cannot do this, but if you choose your parameters correctly, you can preserve energy. Um, but which gets, and hopefully the error doesn't cause too much to um, are less are less strict. Use some energy. Um, um, it's a major. So I was very hopeful for many years. But yeah, there was a key catch. Manifold to be bigger and bigger. The rescan manifold becomes flatter and flatter. Um, as you approach singularity. And this has been the stumbling block despite space. It doesn't lead to blow up on any manifold because of the fact that on the blow up you have to increase the universality. It's so far we can only do that. Okay, but that's well, uh, so that, yes, I think one. Uh, well, so this is to get below. Okay, what are the two? So, and so one of the simplest thing you can do is you can take a product, you put it in kind of warping to get a warp product. Um, where, so we in fact do this all the time. Okay, uh, lots and lots of people study the Euler equation in axisymmetric coordinates, then cylindrical coordinates, and this in cylindrical coordinates are just basically representing R3 as a warped product of R2, which is really a half plane, but basically R2 and a circle. Right? In cylindrical coordinates, the metric is not quite Euclidean. There's a little warping factor R squared in the angular variable. This is a basic example of a warped product. Uh, okay, so you can consider more general warping. Um, and what warping does in the that's what we call axisymmetric, with or without swirl. It really two positive scalar interaction. So it of participity and positive scalar interaction system. So, for example, if you write the Euler equations in axisymmetric coordinates and you assume axisymmetric solutions, you get vorticity is now a scalar, and it gets transported, but not with if it was 2D Euler, vorticity would just be transported with forcing term 0. Here, dt is the material derivative, dt plus transport, the but there's an extra term coming from a passive scalar. So there'll be this other scalar, which corresponds to angular velocity normalized. So and the velocity gets transported by expression depending on the passive scalar. About that's what neutral coordinate. And you can do the same. So any product and can make again a action. And the upshot is any kind of you can modify the equation. So the normal equation is and velocity, but now you can add some quadratic terms to the right hand side, where the quadratic terms involve if you like, um, and there are pretty much prescribe quite a general class of nonlinearities here. So you can basically create sort of arbitrary Booster-Nest type equations into some. So that looks like stability. You just make sure one of these equations, then that will show the sum over embeds that all these terms show up. They turn out to be lower order solution. And so while these flexibility in the limit, when you take a self-similar type blowup ansatz, than the main term dynamics, so it any kind of blowup method, you can somehow generate an approximate self-similar solution, maybe a self-similar solution with a forcing term which is lower order. You might be able to use these extra Booster-Nest type terms to get rid of the forcing term. So you might be able to convert a blowup with a forcing term to a blowup without the forcing term by adding. Okay. So that was one thing that I tried playing with. Is that so there's this sort of dichotomy, right? So on the one hand, the curvature can make it really you want scaling. And so you want the best of both worlds. You want, and so you can take manifolds that are the product and the compact, and you can try to create self-similar in the direction, kind of stationary in the curve direction. So manifold looks like this. Okay. There's a slide rho across n. So there's a whole partially blue equations, which at a given time will sort of concentrate on a like this, and it will sort of compress in the but in the vertical direction, so you still get to use the curvature in the vertical direction. That you can make a warped product where the curvature depends on the spatial position, but if which is converging to become it's similar to the previous thing. Auto just to take a direct product. Again, if you want to eliminate I think. Um, yeah, but the model problem is, uh, I, I, I think that Cordoba and Martin's zero. So in R3, we're able to the small forcing term. Um, show, but with it, so what I have to do to create blow up for in a cylinder with maybe a mild forcing term for starting with just a direct product metric, and then and then this we do zero. Uh, get, uh, right so okay, so the horizontal I'll call X1. Uh, the, so the orientation like it splits up very nicely. So it's just, the horizontal velocity gets transported by itself and also by the vertical velocity, and the vertical velocity gets transported by it and by the horizontal velocity. And there's pressure and there's a divergence street condition like that. So you just right out. The thing that, but the equation simplifies a lot in the limit. Um, the velocity gets a lot smaller in the vertical direction and a lot so the velocity should stay large, sorry, in the vertical direction, but the horizontal velocity should get small. And the pressure gradient should get large in the horizontal direction, but the pressure gradient should be a lot smaller in the vertical direction. So if you want zero, keep it, you can eliminate this term. This becomes zero. And that's really good news because then you can just completely discard the first equation. Okay, so this equation then just becomes the equation for the pressure. The pressure is just the antiderivative, and the pressure doesn't appear anywhere else. So we can just eliminate this equation. And so in the self this uh, equation sort of uh, if it's a steady state or some sort of self-similar type solution to this equation, to the you don't have this pressure anymore. It's like the Euler equation. It's the Euler equation, but with a drift. The block horizontal that's distorted. Euler equation. Or it becomes, it becomes an equation for U1. So the horizontal velocity is just the antiderivative of the negative of the divergence of three in the vertical direction. Um, you can have divergence vertically. It just manifests as creating horizontal velocity, which then uh, um, analytically it's not a great differential equations are for boundary. It has a sort of ill-posedness type structure. Um, that's not a great thing. Theoretically, it's not that bad of a system, and you might be able to construct some nice solutions to the system. Um, yeah, so yeah, it has a nice property. It has a scale invariance. I mean, the original equation. Yeah, so somehow uh, we have now recovered some self-similarity. So even though in vertical scaling, there's a scaling in the horizontal direction that gives you um, some dynamics. it has a conserved energy, which is not surprising since all that has conserved energy. It's only the conserved energy only moves the vertical direction. The horizontal, yeah, in the scaling limit, the horizontal portion has vanishing energy. All the energy is wrapped up for motion. Okay, we have so I haven't worked out what that is. I think what would be very interesting is to try to construct some interesting either stationary solutions or solutions to this equation. Uh, so if you blow up solution to this equation and still the force solution to the original, yeah, to reinsert, which we got rid of. Um, by the metrics, maybe so would like to create sort of blowing up. Uh, uh, I don't, but you can try separation of variables. Okay, so these are functions the x1 and the vertical x. But I try to separate looking at the ansatz function. Yeah. You can write down for this answer. So this ansatz requires a scalar function, v, for the horizontal velocity, and two vector fields, v alpha and w alpha for the vertical velocity. And if you want, you can introduce the so the this so you pass into this model equation, and you get and this is the system that okay. So yeah, so the yeah, so the you have these two velocity fields. You contract them against the one forms, and you get these three equations, which are which these are the main equations trying to tell you that the from the horizontal velocity and so forth. This symbol is I think what people put is contraction. So in the other talks it's for like iota w theta. For there to be a trick on a vertical trick that is consistent with um, so there's three vector equations and two scalar conditions. So in principle, this is a system. There are four unknowns: v, w, lambda, theta. If one is d dimensional, so your dimension is big enough, like this system should have solutions. And it forms and vector field. polynomial with some number of coefficients, variables, and I could just get an exact prediction of the system. I expect to do naively to like 200 variables. I need to simplify this system so we can hope that solutions exist. Um, but I do feel like this scheme has it do seem to be very this particular system. This system. I mean, scary, right? I mean, this was um, well, so that's the, my dream. So hoping one here gets good at manifolds, get interested in this sort of problem. Okay, so I think I will stop there. Thank you.